Hello and welcome to helpyourmath.com. In this video, we are going to take a quick look at factoring sums of squares into complex roots. Because just writing cannot be factored sometimes just isn't good enough. A review of the difference of squares. So you might recall that a difference of squares is a perfect square minus a perfect square. So the difference is the subtraction and then the two terms are the two perfect squares, and they factor into what are called conjugates of each other. They're conjugates because we have these two things, this x and y with a subtraction sign between them, and the x and y with an addition sign between them. Any difference of squares will always factor into factors of conjugates of each other. That's just the nature of the game. So we know this, we love this. We've seen this before when we've factored x squared minus 25. X squared we can recognize as a perfect square, and its root is x. And 25 is a perfect square, and its root is 5. So this will factor into, we could rewrite this as x minus 5, root minus root, times root plus root. Well, as we take a deeper look into polynomials, it's nice when they do have real number factors, but that's just not always going to be the case. So let's review the subtraction rule. When we're subtracting any two integers or any two numbers, and we have, let's say, 7 minus negative 15. When we want to write subtraction as addition, we can do so by adding the opposite. Adding the opposite. Well, it turns out, so just the same way we could rewrite this as 7 plus positive 15 and get an answer of 22, we can actually kind of do this in reverse. We could take a nice addition, let's do 7 plus 15, and we could write it as subtraction. It's kind of like doing the opposite of this rule. So I could, if I wanted to, rewrite this as 7 minus the opposite of positive 15, negative 15. Those two expressions are equal expressions. They would provide the same result. Now let's put those two ideas together. First, let's take x squared plus 25 and rewrite it as subtraction, right? This is currently what I would call a sum of squares, which does not factor into real factors. So let's see, if we rewrite a subtraction, just like we did, we're going to take x squared, we're going to rewrite plus positive as minus negative. And now we have, at least the x squared is a perfect square. Let's talk about negative 25 and what its root is. So if we want to take the square root of negative 25, I would split up the negative from the 25 and say that's negative 1 times 25. Well, the square root of negative 1 using complex numbers is I, and the square root of 25 is 5. So I'm going to put the 5 in front of the I, and there we go. So now I could say, okay, well, here's x squared, and negative 25 is 5i squared. That's an I, sorry, there we go. And we've created a subtraction, so now we kind of have a difference of squares, complex squares, but squares nonetheless. And we could take this and say, well, this is the same as this, and this would factor into root minus root times root plus root. And we can do this, there it is. So factor x squared plus 25, we just did that, x minus 5i times x plus 5i. We could do this again with x squared plus 81. First, let's get this to be a difference of some kind of squares, complex or otherwise. This would be x squared minus negative 81, because we can take that addition and rewrite it as subtraction by subtracting the opposite. Then we know that x squared has a root of x, negative 81. So the square root of negative 81, well, that would be negative 1 times 81, and that would be 9i. So this would be 9i quantity squared. So we could factor x squared plus 81, I'm going to put that over here, root minus root times root plus root. Now, we looked at two examples where the second number is itself a perfect square, but we can also do this when the second number is not a perfect square. And we could also do this with the regular difference of squares. We can apply that formula even when the second number, or one of the two numbers, is not a perfect square. Let's take a look at this one. So we're going to rewrite this as subtraction, y squared minus negative 7. And then we know that y squared has a root of y. Negative 7, So the square root of -7, there's not much I can do. 7's a prime number. It's not a perfect square. But I can say, well, the negative under the radical, let's pop that out. That negative is like -1 times 7. The square root of -1 is I. I like to put my i's in front of my radicals. I just caution you, if you do put the radical first, I suggest that you like kind of hook the end of it. So write it as the square root of 7, because we want to be very clear that I is not under the radical. It would be incorrect to put I under the radical. You want to make sure it's very clear. That's why I put it in front, so that way there's no mistaking whether I is under the radical or not. It's definitely not. And then this, we have a root of I root 7 squared. So this will factor into, we're going to rewrite this as root minus root times root plus root. Gross, but hey, it works. And lastly, what if we have m squared plus 12? Well, m squared plus 12 is m squared minus -12. M squared would just be, well, m squared. And then let's talk about the square root of 12. I'll come over here. The square root of -12. This would be I root 12. However, we could simplify the square root of 12. It does have a perfect square factor of 4. So I would take the square root of 4, which is 2. 2 will join the I out in front, and we're left with that radical 3. So we would say the square root of -12 would be 2I root 3 squared. And then this would become, let's see, root minus root, am I going to be able to squeeze this in, times root plus root. Almost. And there we have it. We were able to figure out a way to factor a sum of squares. It did involve some complex roots, but we got there. Thank you for stopping by.